Hello everyone, myself Vinay, and today we're going to discuss a topic of signals and systems, and the topic is Laplace transformation in control system. So, first of all, it is the content of the video that we're going to discuss. Firstly, we'll talk about like what is Laplace transform. Then we're going to discuss about the uses of Laplace transform in control systems, and then at last we'll discuss some applications of Laplace transform. So first of all, discuss about what is Laplace transform. So it is a mathematical technique that is used to convert function from time domain to frequency domain. So for example, you are given a function f of t. So you can apply a Laplace transformation and you'll get a function in f of s. So it's a frequency domain. So you are thinking that why we are like transforming the function from time to frequency. So for example, you are given a very complex function, like equation like second order differential equation or third order differential equation, and you are facing issues or like you are not able to like solve that equation, so you can apply Laplace transform there. So basically you have to just apply Laplace transform on that equation and you will get a linear equation in the frequency domain. You can solve that equation and get the output in the frequency domain, and then you can apply the Laplace transform back on that equation and you will get the equation the solution in time domain back. So it is used to like simplifies the calculation and analysis of linear dynamic systems. About control systems. So what are control systems? So control system is a system designed to regulate, manage and control the behavior of other system, processing or adjusting the inputs to maintain desired outputs. Like so it's a bookish language. So in simple words, I'll explain that. Control system are the system in which you can change the input to get a desirable output. um, Everything like surrounding by you is a control system. For example, the example mentioned here is the like bread baker or toaster. So in this, the input is a timer level. You can adjust the timer level so that in each different timer level, you will get the different color of the bread. Means, for example, the timer is high, the bread is baked more and the bread color is more brownish. And if timer is low, then the bread is baked less and the timer is like sorry, the color is less brownish. So it is a control system. Like you're controlling the input to getting a desirable output. Like in daily life, you are using like a socket, for example. Socket is a control system. If the input is positive, like switch is closed or if the switch is on, then the electricity will be provided. And if the switch is off, the electricity will be not provided. So it is also a control system. The phone, the television, the laptop, all of these function like devices are the control systems. So now we'll discuss the use of Laplace transform in control systems. So first of all, system modeling. So system modeling, for example, you can see that there is a complex circuit, hmm, and the input is this and the output is this, and you have to solve it. And while doing system modeling, you are like changing the inputs multiple times, like and looking for the outputs for multiple times. Like for example, you're changing the input by some values and tracing or like plotting the outputs so that you get to know about the systems. But you can see that for a complex system, it is very difficult to calculate each and every time. So what we can do that we can use a transfer function. And firstly, we'll like calculate the output equation, and then we will calculate the input equation and convert them into the like frequency domain, and then we'll get the transfer function, and the transfer function is the output in frequency domain divided by input in frequency domain. So transfer function is very useful because it makes the calculation very easier, and you don't have to calculate the same function multiple times. Despite you can just calculate the transfer function and change the input and you'll get the output by doing very less calculations with respect to that. So it is very commonly used in that. Let's discuss about the second point, stability analysis. So you can like analyze the stability of a system by using Laplace. So if pole zero analysis, so the location of poles and zeros in the S plane determines the stability and performance. So first of all, we'll calculate the transfer function of that system, and we'll get a, numerator and denominator, like output and input. So poles are the roots of the equation of the denominator, ds is equals to 0. Okay, or the like input ds equals to 0. And zeros are the roots of the equation output, or ns equals to 0, numerator equals to 0. So if the poles have a negative real parts, because the like the as you know that the like frequency domain equations are complex equations, and you'll get these roots are complex roots. So if all poles have a negative real parts, the system is unstable. Sorry, stable. If the pole has a positive real part, the system is unstable. And if poles are on the imaginary axis, like this is also a probability, then system may be stable or may be unstable. For this, you have to do further like calculations and all. But like for keeping this video precise, we are not deep diving into that topic. So these are the basic things like you can use to analyze the stability of a system. Then control designs. So Laplace transform is also used in design controllers. Example PID controllers, petro interrogative derivative controllers. So these are the controllers that used in industries to like regulate or control the flows, or like flow, temperature, pressure, and all of things. And it is mainly used in industry by control engineers. So let's talk about the real world application of Laplace transformation. So in circuit analysis, it is commonly used. For example, you are given a circuit. You can convert this circuit into this circuit by applying Laplace transformation, and the Vs is equals to RIS. So like it's a basic circuit, so you have not in inductive circuits like you are give the inductive circuit and time domain is this, and but when you change the domain in frequency, the circuit will be changed into this, and it is very useful because it's a linear circuit, and you don't have like in general time domain you have to differentiate or integrate, but in this you don't have to do that much calculation. You just have a linear equation. Okay. In capacitive circuit also you will get the equation in like time time domain frequency. I guess you are not able to see that we discovered. Okay, is that part. Okay. Uh, then solving differential equations. The Laplace transform is also very useful in solving very complex differential equation. For example, you are giving a differential equation. Like I, first of all, I will go to the framework. How can you solve? Then I will go through an example also. Like how can you do that? So firstly, if you're giving a differential equation with an initial condition, you can convert into algebraic equation by applying Laplace transformation. Then you can solve the equation. Then the solution you will get in the like frequency domain. You can apply inverse transform and you get solution in time domain. Okay. So here is the example. It is a like basic first order differential equation, and the initial condition is given. You are applying a Laplace transformation on both of sides, and you'll get this equation. Like these are the like, basic transformation. You will have to like remind or learn that basic transformation. Then uh, you can like solve this for the ys, and then we apply the inverse Laplace transformation again on this and get the final solution in time domain. So you can see that it is very convenient for higher order like differential equation to solve. So there are some real world applications also, like automotive systems, suspension and braking control, or like ABS system like automatic braking system, or you can like cruise control systems that like which is very popular in these days in cars. In these systems, we use Laplace transformation to easier the calculations for the for the system, and so that we can do the calculations precisely. In robotic arms, you know that we have to precise with each and every movement of that arm. So Laplace transformation is used to calculate the you can say that equations. For example, at how much angle we have to move. So for that calculation, we use the Laplace transformation to easify the calculations and precise the motion control of that arm. Industrial automation, like regulating temperatures, pressure, and flow. We already told you about the PID controllers. So in PID controllers are generally used in industries or by control engineers in industries, and it is very commonly used to regulate the temperatures these variables, and it is very useful in that. Okay, the lap. So at the end, we can say that Laplace transform is play very important role in improving the system accuracy, stability, hmm, uh, and we can use this mathematical tool to easify the calculations and easify the calculations of control system, and we can solve complex to complex equations by simplifying them. Also, by transfer function, engineers can identify and compensate the factors that are reducing accuracy, such as time delays and undecided oscillations. So, for example, you have calculated transfer function of a means a system. So you know that that this variable will be reducing or improving the accuracy. So you can change or compensate that factors by applying some other variables in that input, or you can change compensate that factor. Okay, with Laplace based models, controllers can be tuned to meet specified accuracy and adjusting parameters to desired responses. Okay, so so that's all from my side. Thanks for watching this. Thank you.